So you can hear me okay? I should start talking? Okay. Okay, so hopefully you can all hear me or translation and see my slides. So I'm going to talk about taking a scientific approach to physics education. And I'm going to start with a general introduction to some basic ideas about how the brain learns complex thinking, then show how people like myself and other researchers have been applying these ideas in university classrooms in physics and measuring the results, getting data and principles from these. And then I'll focus in on some detailed findings about different ways, types of instruction that we've found improve learning and why. Now, this is targeted really towards teachers, to what research can tell you about how to maximize the learning of your students. But if there are students in the audience, this still applies really to you, and it's really covers the thinking that you need to do to maximize your learning and really how to exercise your brain to develop better capabilities in thinking about physics. Now, before I get into the details of this, I want to give you a little background about how I got involved in this kind of research and thinking about education this way. And it didn't actually come from my teaching classes. It came from my working in my atomic physics research program that, of course, I had for many years. And I saw a pattern that was confusing to me, which was that these new graduate students in physics, they would had many years of success in their physics and math courses, but when they would come into my lab, they didn't seem to really know how to do physics. But there clearly wasn't anything basically wrong with them, because after just a few years of working with me in the lab, they had turned into expert physicists. Now, after I saw this happen over and over again, I decided there was just some fundamental puzzle here about thinking and learning. And this was 30 years ago. So I tackled it as a science problem. And I looked into what do we know of the research on how people learn, particularly how they learn and think about physics. And after a couple of years of reading lots of papers and thinking about this, I came to understand why this was happening. It really wasn't a puzzle. It made sense. It also made me realize there were much more effective ways to teach than what I and all of my other faculty colleagues were using. But it also then got me started in doing this kind of research on science education, doing experiments, collecting data, establishing basic principles, and so on. And now it's almost 200 papers later on that. But all of my research in this has really been focusing on what I call expertise, the thinking like a good scientist, in particular, a good physicist, how they think and how you learn that kind of thinking. And so that's what I'm going to talk about. But there's, over the past couple of decades, there's actually been major advances in how people learn this kind of complex thinking. And it's coming in three different fields that fit together nicely. The cognitive psychologists who study very basic level how people think and learn, brain research and imaging nowadays, and then people like myself who do these kind of studies in university science and engineering classrooms. And at the most basic level, it's really caused us to rethink how learning really happens. And the old and current model, current in all the universities around the world, is really that these student brains come into our classroom and they vary in different ways, and we immerse them in knowledge, and that knowledge soaks in different amounts depending on what that brain was like originally. And so with this model of learning, the focus has always been on selecting the best brains, all these entrance exams and requirements and so on, and then also deciding what to put in the knowledge soup that we're putting them into, what topics are covered in what order and so on to soak in the best. Now, this model has been around for a long time, but it's just wrong. That's simply not how this kind of learning works. And what the modern research is telling us is a very different view, which is these brains and at the university level really aren't very different, but they're quite changeable. And it's really, they transform through the educational process. Quite literally, the neurons are hooked up in different ways as a result of the intense thinking that goes on in a good education. And it's really this rewired brain has improved capabilities. And what this means is that good learning is really not about putting knowledge into a brain. It's really about developing the capabilities of that brain. Now, we can, with brain imaging, we can actually even see this. This is two images here. One of them is there are two people that are interpreting a medical x-ray. The brain on the right is a medical student who's just learning to do this. The brain on the left is a highly trained expert radiologist. And you can see as a result of his training, his brain is activated in a completely different way in carrying out this task. And so what the research is telling us is that the learning is really about developing, enhancing the correct neuron connections. And so it's really very much like developing a muscle. Just as with a muscle, if I want to build up a muscle, the intensity and the type of exercise is really critical to how it develops. And that's exactly the same in developing these thinking capabilities in the brain. And one very basic thing the research says is the brain really only learns what it practices intently. And that's really to get the right kind of mental exercise, to get the right kind of mental connections in the brain. And so the rest of my talk is really how to develop the brain so it's able to think more like a good physicist. And so we've now applying these very basic principles in classrooms in a very variety of ways and looking at the results. And so I'm going to give you an example of one of many such experiments carried out by my group and many others on this, but this is one I was involved with. And so we were looking at a very large introductory physics class. It was one that needs required to be taken. All the students who are planning to go into engineering and science. And it was so large, we could take two sections of this class with 270 students each that measured them very carefully, and they really looked very identical, the two distributions. And then we taught these two classes were taught in different ways. The control class was taught by a highly experienced professor with good student ratings, but he used the standard lecture approach I'm sure you're all familiar with. Instructor stands up and talks, and students listen and take notes. The experimental class was taught by someone who is a fairly new PhD, but trained in my program in the principles and methods of this kind of research-based teaching. And so these two instructors then agreed to cover the same material in the same amount of class time, and then give a surprise test right after the end of this section to see how much the students had learned from coming to class, listening to these lectures. Now, the experiment, I'm sure you all are familiar with a traditional lecture, but the experimental class, what happened in it was first the students had a little short pre-class reading assignment to give them basic facts and terminology. But then class wouldn't start with giving them information. It would start with a question like this. You have this circuit with batteries and light bulbs, and what happens to the brightness of this bulb when that switch is closed. And every student has, in this case, using a mobile phone to answer this. They could submit what their answer was, and the instructor's computer records who they were and what answer they chose. And the instructor can see what the selection of answers from across class was. Now, at that point, they weren't told what the right answer was, rather, or even shown what the vote is. Rather, they were told to talk with their neighbors and re-vote based on that discussion. So in a big lecture theater like this would be just the students on each side of them. And while they're having that discussion about what answer was right and why, the instructor's circulating up and down the aisles, listening in on those conversations, getting little snapshots of what's going on in those students' brains, what aspects of their thinking are like a physicist and what are not. And then the instructor does demonstration, shows the result, but then has a follow-up summary where it's not lecturing, it's giving them feedback on their thinking, on which of their models about the physics and the reasoning was correct and which was incorrect and why. And I emphasize the incorrect and why because that's what cognitive psychologists tell us is when most learning actually takes place. It's not when one's told you did something right, but when you are helped to understand why you're thinking about something incorrectly and how to improve that. Now, okay, so that was an example, one kind of question, but in this class, there are also more mathematical topics, and there students would write out simple answers on worksheets, but the same sort of process of discussing and voting. Now, if you think about what they're doing in answering questions like this, they're practicing thinking like physicists. I mean, to do that electricity question, you have to think about what your conceptual model of electricity is, how it applies in going through a light bulb, and apply that concept in this particular situation and run models to test that. You've got to evaluate the reasoning of both yourself and your fellow students that might be different. So all of these are just the same kind of thinking a physicist does in all their different aspects of their work. Now, one important additional factor in this, though, was while the students were doing that, they were also getting feedback to guide and improve their thinking. They were getting it by comparing their predictions with what actually saw it happen, getting it from other students, and getting it from the instructor, who's now much more informed about their thinking than in a typical class. And so you have this cycle of practicing the thinking you want people to learn, getting feedback on how to improve it. That's really at the fundamental heart of how one develops expert thinking. Okay, so that's just an example of what was one done, but of course this was part of an experiment. Both sections were given this surprise quiz to see how much they'd learned. And so here's the results of this quiz. So this is the score across this way, number of students on this axis, the histogram. And you can see a profound difference between the experimental class and the learning in the lecture class. Now, in fact, the difference is a little bigger than you might guess, because on this particular test, random guessing would give an average student on average 3. So you really have to look at the amount of learning as kind of how far above 3 they are. And when you realize that, you realize how tiny the amount of learning from lecture was. And this is characteristic. I've done many other experiments, as of others, to see this same sort of phenomena of how little the standard lecture actually achieves in learning, but it also, with this experimental class, not just shows there's a big difference, but I want to emphasize how you can see in blue, the entire distribution moved up. So this isn't a way of teaching that's particularly good for the weaker students or the stronger students. It's really better for all the students with a human brain. It's really how the brain learns. Now, just to show you that wasn't anything special in that class, this is a different subject, different instructors. This is from work done by Beth Simon at University of California, San Diego, looking at their 4 introductory computer science courses, where they took the same instructors, and one year they lectured and had been for many years, and they looked at the failure rates in these courses. And then all these 4 instructors switched over to teaching very much like I just gave you the example in the physics class of giving them questions to answer, talk with fellow students, and so on. And across the board, for all of these courses taught by these same 4 instructors, just using different teaching methods, their failure rates dropped dramatically. And so now they have the same instructors, but just because they've learned better teaching methods, they have about 1/3 the failure rates they did before. And I could give you many other examples of research like this. Now, most of this work's been done in introductory courses, but my own group and a few others have now started applying these same principles in the more advanced courses taken by physics majors. And these are just examples shown here where most of this work, they're, highly mathematical calculations, things. And so they're writing out, working out solutions, but again, working in small groups with the instructors circulating around, monitoring, giving the feedback to them as they're doing it. And so we actually, most of the courses now taken by physics majors, and they're up, beyond the introductory level, are now taught in this fashion. It's even been applied in advanced graduate courses with considerable success. And in all of these courses, the basic structure is actually the same, and seems to work well across all the different size courses and different levels. The students do some basic preparation for class, and then during class, they're working through these activities, given difficult questions to work through and answer, working in small groups, while the instructor is circulating, monitoring how they're doing, answering targeted questions. And then at regular intervals through the class, the instructor will pull the whole class together and give them feedback based on how they're doing, helping them out, bringing all the students kind of up to a similar level. And then the students continue working through the next part of the problem or worksheet they're doing. But all of these things have these same essential features of the students are practicing the thinking you want them to learn, and the instructors are giving them targeted, timely feedback on their thinking, how to improve it. Now, I'm going to suddenly switch here then to a problem I've been working on more recently, which is that, as I showed you in this distribution, we had, the distribution moved up dramatically compared to the traditional lecture, but there was still a big distribution. There's a lot of students down here, and we want to move all the students up to the top. And so we started worrying about how to do that. And I particularly started worrying that with Stanford students when we found that, Stanford's an extremely selective institution, probably the most selective in North America. And so every student is good. Why aren't all of them being highly successful in introductory physics? And so we've been studying this and looking at a whole bunch of different factors, changing teaching methods, et cetera. And we got data on lots of things and lots of fancy analysis and to try and understand why and what was preventing us from compressing that distribution all up to the top. And we ruled out a lot of things, but what we found out is that really it was incoming preparation that made all the difference. And so, in particular, people were worried about historically underrepresented minorities getting lower grades on average, or first generation low income students or female students compared to the Caucasian males and Asian students. And so there were all these differences in grades, but when we did these measured control of basically incoming preparation in math, but mostly in physics, all of these differences went away. And so what it showed was that, and basically for any given person in the course, incoming preparation in physics made a tremendous difference on the success of students in the class. And this is really important because the introductory physics is really a very large barrier to students being successful in their pursuing a career, a major in physics or almost any engineering school. But if you look at the measures of incoming preparation, in fact, we have a short 30-minute diagnostic test that we have now. We can basically explain a very large fraction of the variation in student grades, and we can almost perfectly predict sort of, on the first day of class, who's going to be at the top 10% of this class and who's going to be in the bottom 20% and fail it. And so, but it's important to emphasize this isn't a measure of their intelligence or capability or work ethic or anything. It's really just a measure of what physics they had been taught in their secondary school. And basically what as we've dug into this, the funding of education in the US is such that wealthier areas have much better physics teachers, and those students learn more physics, and then that is carried over into their college teaching. And so we're really, we thought, well, maybe this is just funny about physics, but we've looked at other universities with very different student populations, and we find very much the same dependence on incoming preparation. So what we find is it's really clearly not the students, it's the way introductory physics is taught. And what we see is that it's optimized for the coverage and pace for really the top, most highly privileged, best educated students coming into college. And it's really, discriminating and harmful for the ones who didn't happen to be fortunate enough to go to wealthy secondary schools with, spend a lot good teachers. And so it's made it very clear that to be effective, one needs to have both good teaching methods, but you also have to match the curriculum to the students and what they are coming in knowing and not knowing. And if one did that right, we could make many more students be successful in careers in science and engineering. Okay, I'll skip over. There's lots of studies showing these things, but I won't take time on this. I want to then just look to the last part of kind of giving you a summary of what all the kind of research from physics classrooms has told us on what things really help to improve learning and why. And these are sort of things you can think about using in your own teaching. Now, this figure here sort of summarizes a whole lot of research and categorize it. And in the middle here is really the part that's really essential, which is that the students have to be practicing the thinking. And that really means practicing making decisions using that physics knowledge, making the kinds of decisions that physicists make in solving problems. And they've got to be practicing that with good feedback. The feedback that's timely, it's specific to what to improve, and it's actionable. So they can be practice and improve and then go back and practice more. And so that's what has to happen. But then there's a lot of things that have to go into the design of these practice activities. They're along the top, and I'll talk more about them. And then there's some things that we know about have to go into most effective implementation in actual courses along the bottom. And so the things that go into good practice task design is the disciplinary expertise you want them to learn. It's got to match and build on their prior knowledge and experience. You can't have first-year beginning students and expect them to learn quantum field theory. You've got to start at a reasonable level. There's motivation is very important, to motivate them to put in the necessary intense mental effort that's important for doing the kind of brain rewiring that's needed. And there's some basic constraints about how the brain works. So I'm going to talk a little more about a couple of these things, just to give you a better example. The disciplinary expertise is something my own group has been studying. What does that really involve? And over the last few years, my group has been studying how experts in science, engineering, a little bit in medicine, solve authentic problems. So how physicists in their day-to-day work actually what kind of physics problems they solve and how they do it. And we found that we could characterize this problem-solving process based around a set of decisions they have to make in the problem-solving process. But what was really surprising to us is that as we studied across close to a dozen different subfields of science and engineering, we found they were all using the same set of 29 decisions. Now, that probably seems crazy to you, that somebody in biology or mechanical engineering would be doing the same problem-solving decisions as you would in physics, until you look at what those decisions are. They look at what the initial problem is, and then they decide whether the concepts and models that are relevant to that situation, what information is relevant, what's irrelevant to a solution, what assumptions and approximations are appropriate, deciding on what potential solution methods to pursue, and that's usually almost always based on their past experience with deciding on what are related problems they can use. And then this carries through down to once they have a solution or a conclusion, deciding does it make sense and deciding on the different ways to test that solution. So everybody's, start thinking about this, it's not so surprising that each one of them are having to do this. Now, I want to emphasize, even though they're having to make the same decisions, like, what information is relevant, how they make the decisions, that requires them to use very specialized disciplinary knowledge, and those decisions are made in very different ways depending on the subject area. And we see that these experts have that knowledge or really organized in a way that's optimized for applying it to making these decisions. So if you look at these kinds of decisions that you want students to learn to make, that they need to be practicing making in order to learn to think like a physicist, you need to have some authentic problem context, and you need to have them practicing using their physics knowledge to make these decisions in that problem. And that's really what's necessary to exercise their brain in the right way to make them better physicists. But if you think more about those questions, those decisions that I have listed, and then you look at what are they in any textbook I've looked at, you look at what are they required to do in the problems in the textbook or on any exam problem. All those questions, all those decisions are actually removed. And so as a result, students learn information, they learn to memorize procedures, but not how to use those ideas, how to use that information to actually make decisions and solve problems. And so if you go back to my whole original puzzle that I started with is, why could these physics graduate students do so well in physics courses and not be able to do physics? This is exactly the reason. They had learned lots of physics information. They weren't able to use this to do physics. And just to make this contrast a little clearer, I'll give you an example here. I mean, this is every student in introductory mechanics, physics 1 sees this Atwood machine where you've got masses, and then you're told to calculate the acceleration. Normally in the book, it tells, okay, assume the strings are massless and the pulleys are massless and there's no friction in the problem. None of which are actually true. And so as a result, there's no decisions involved in this problem at all. It's just plugging into a procedure. And so this is good only for learning to do well on physics exams, not good at all for having to learn to think like a physicist. Now, here's a contrast that I would give you that still covers much of the same material of physics 1, but it's a very different, it requires a very different kind of thinking, okay? So here saying, okay, you're building a tree house, you need to pull, lumber up to where you want it. How much weight can you pull up? How strong does the rope have to be? And is it worth the time and money to actually go get a pulley, or is it fine to just have the rope draped over a limb like this? This is let's call it an authentic problem. It's a problem somebody would actually care about the answer as opposed to the Atwood machine. But it also requires many more decisions to make. You've got to decide what's important. You've got to come up with how to find the relevant information to solve this and make judgments about how precise and appropriate that information is and what you can conclude from it. And all these different things that really require the thinking that, like a physicist, like any good scientist, would need to solve meaningful problems. And so really, from a student or an instructor point of view, you need to be practicing solving these kinds of problems with all the complexity and the challenges and the thinking involved in them. Okay, let me just skip over here to brain constraints. And this is something that's quite fundamental, but almost no university instructors know about it, but it's really important. And the main one that's important is how the memory works. And it turns out that if you think about the way memory in the brain works, a simple model of this is, first, there's two parts to it. The one part is what is called the long-term memory, and it's what most of us think about as memory. It has a tremendous capacity. We can remember many, many things, and for a long time, days, years, decades. But it turns out that things don't information doesn't go into long-term memory immediately. It has to go through what's called the technical term, the short-term working memory. It's really a buffer for information as it comes in, goes through this buffer before it can be processed and go into long-term memory. Now, the short-term working memory is very different in that it has a very small capacity. The typical human brain's about 6 items, and it works on the time scale of minutes. And it's really sort of how much and how long the brain can pay attention to something. Now, if you think about this, this is tremendously important for what's happening in the classroom, where students are getting lots and lots of information, typically vastly more than this. But because of this limited capacity, when you get some new thing coming in, it pushes out something that was already there, and so it doesn't get processed and put into long-term memory. So this is extremely important in the context of what students can learn actually in the classroom, where they get lots of new information and it's on a short time scale. And to recognize, and this has been very extensively studied by cognitive psychologists, that every additional new thing that comes in basically reduces the process and learning that you want. And so you have to look at what sort of things add additional load on this working memory. And one of the biggest things is split attention. And so if students are looking down at their mobile phones or their computers in class, checking email or something, this is an absolute disaster for learning. And it's even worse online because there's more things on the computer screen for them to be looking at the same time. And the worst part about this is the human brain is really bad at recognizing how seriously splitting their attention has on their actual learning. So those of you who are getting bored listening to my talk and you're checking your incoming email and messages, you're not going to remember any of this. Now, split attention is something the students can do, but there's also a bunch of things instructors do which put unnecessary load on the working memory and hurt the learning that your students have. Examples are using jargon that's not highly familiar, even if you've defined it to them. If it's not well established in their long-term memory, every time you use it, it uses up their working memory to process it. Or, if you want to illustrate something, and a lot of times instead of some very basic illustration, people will dress it up to make it look prettier, have some nice background pictures or something around it. If that draws students' attention to look nice, that actually hurts their learning. And part that really upsets people when I say it is those interesting little stories or jokes. If they draw a student's attention to them, they actually hurt their learning of the material you care about. Now, there's one other important aspect of how the brain constraints that are important to keep in mind, which is when you look at long-term recall of information, obviously that's what we care about, is students learning something and then remembering it, using it appropriately much later. So there's problems with getting things into the long-term memory, but an even bigger problem is recalling it when you need it later on. And it's important to recognize that what causes the biggest limitation on recall is the additional stuff you learn after you've learned something. When you learn more things, it makes it hard to recall the first part. Now, this is very important in the teaching setting, because the traditional way we would teach physics is, we covered chapter 1 and we have students do problems on it and tests on it and so on. And then we figure, okay, they've learned that. Now we go on and do chapter 2 and then chapter 3 and so on. And the problem is that, in fact, if you test them carefully, they might have learned chapter 1 pretty well, but by the time you've covered chapter 2 and 3, they will have that had a lot more trouble recalling chapter one because the interference of the new stuff they've learned. And so now one of the things the research shows is that it's pretty easy if you recognize this problem. It's pretty easy to reduce this interference of new learning, of recall. And that's, you just have to do it by, as you're learning new things, you have to the brain has to periodically go back and think about the other stuff. So as you're doing chapter 2 and 3, every now and then you go back and think about chapter 1 again and how it's similar or different. That cleans up these basically interfering neuron connections. It's kind of analogous in my mind to doing a quantum measurement, getting rid of the decoherence. And I'll just a note to students, this is something you can routinely do on your own as you're learning new things, even if the instructor isn't having you do it. Okay, so I'm just going to finish up now with a couple of comments on the implementation of these kinds of activities in the classroom setting. The one is just, okay, I told you students have to be practicing things, given tasks to do, they're working in small groups and so on to do this. But it's really important that they have very clear deliverables. So it's not just enough to go up and think about something or figure out an answer. They have to be very clear that they have some job they have to complete, write out answers to explain things, justify, etc. Something they have to complete, turn in, instructor can look at. But the other aspect of implementation is this social learning. What we see is that in a normal university classroom environment, and secondary school too, actually, the most effective learning is when the students are working in small groups, in groups of 3 or 4, to complete problems. So they're having to do individual answers, but they can discuss the answers, the problems with each other as they're doing it. And this is puzzling to a lot of instructors who don't know about the research behind this, because it's puzzling because why should it be that if I'm talking to some fellow student who doesn't know the material very well, how can that possibly be better or more useful learning time than to hear the explanation from the expert instructor? Now, you can argue, one hand, oftentimes students can better understand another student's confusion and address it, but a really good instructor can still do that. But there's really something else going on here that's really interesting, and this is that this has been studied a lot, and it turns out that the brain sort of has a bunch of processing set up to deal with social interactions. And as a result, when a person's called upon to teach something or explain to somebody else, or even plan to teach it to somebody else, that really triggers or brings in a new additional cognitive processing that the brain sort of has the capacity there. And when they measure that actually produces learning all by itself, additional learning all by itself, compared to what a person has when they're just trying to think about figuring something out on their own. And of course, it's also very useful as a teacher to listen in on those student conversations in the group to have a better understanding of what the student thinking is, and so you can be a more effective teacher. Now, for the students in the audience, I want to just emphasize that one really helpful learning technique is if you're learning some new complicated physics thing, try and ask yourself, go through the exercise of thinking, how could I explain this to my 14-year-old neighbor, and try and think how you would explain this concept to them. That will actually help you understand the concept. In fact, in my teaching physics, I oftentimes give that as a homework assignment that students have to do. Okay, so I'm just going to finish up here so we have time for questions. Um, the conclusion is that research, we have a lot of research over the past 20 years showing good teaching, design, and implementation that gives really much better learning than of physics, and particularly being able to think like a physicist as opposed to just knowing lots of physics information. Better learning of how to think like a physicist, and we really understand the why of this now, the principles, how the brain learns and functions that make these things better. Now, okay, but before we start the questions, I'll pose a question that I always get anyway, so I'll start out, which is that, and I'm sure a lot of you are thinking this, is that you're thinking, oh, he's saying that lectures are terrible and they can't be all that bad because here I was learned from lectures and I became a successful university professor. But the point to keep in mind is this is exactly the same reasoning and logic that was used to make bloodletting the medical treatment of choice for literally 2,000 years. And it was only when one took a scientific approach to medicine that we found there were much better ways to treat things. And the proper medical approach is not just if you give a person something, do they get well or do they die, but to do a proper comparison group of having two equivalent people and you give one of them the treatment and you see, does that person get better compared to the other? And so, anybody who thinks, well, lectures must be good because I had them and I was successful, you really have to think, you need to have an identical twin who went into physics who did go through lectures. They could well have been more successful. So with that, I'll stop and open the floor to questions. If you want to learn more about this, here are some of my favorite references. These are books on learning particular. And in this website here, we have a lot of short 1 or 2 page target things for implementing particular guidance on particular teaching practices and methods. And then here's a paper where we have it's a recent paper going through really the expert problem solving process and this set of decisions that I would urge you to think about including these decisions in what you're asking students to do and what you're covering in class. So thank you for your attention. Okay, I don't hear anything, so. Okay.
Hey there.
Yes.
So yeah, there's some. No, very cool. Sí. Entonces que muteen. Me hacen una señal. Yeah, I hear you. Can you hear the microphone?
Yes.
But can you hear that microphone? Okay, I'm going to mute. Report.
I'm not hearing anything now. If somebody types questions into chat, if you can hear me, if you type into chat, I can answer from that. But okay. Yeah, so okay. The question I have is that someone is a student and possible future teacher. How does the preparation of classes change the preparation time versus research time? So what we found is that it does take some time for instructors to learn to use these methods to teach. Um, Roughly 50 hours of training and practice. Once they've learned how to teach this way, it doesn't take any additional time compared to standard lectures. And in fact, we found that it takes, on the long term, it takes less time because teaching this way, developing these practice activities, actually, people are much more comfortable and much happier using the same activity over multiple years and actually taking other people's practice activities and using them in their class. That works much better than trying to take somebody else's lecture or lecture notes. And so I say it does take a non-trivial amount of time to learn. Essentially, it's pretty equivalent to the time of one university course. But then after that, longer term, it takes no additional time, I would argue, and possibly less. So this question is, how well does this fit into other fields and teaching and other subjects? That's a really good question, and we don't have the data to answer that. These kind of methods have been tested a lot in science. They've been tested a fair amount in engineering. People see that they work in very much the same way, and they give the very similar results across these fields. Nowadays, or just recently, more people in social sciences like economics, somewhat sociology, and so on, and they're finding that they seem to be much the same. There is some good reason, though, to think that the very basic principles apply quite generally. And that has to do, the research that I use to support that comes from the general studies of expertise, the work by one of the references I gave, Anders Ericsson is a cognitive psychologist who studied expertise across many different fields: chess players, musicians, medical, and so on. And he's really made the strongest arguments, and he's been able to show that this basic idea of intently practicing the thinking or skills that you need to learn applies, and getting feedback on how to improve. That seems to be a very universal aspect of developing expertise. And so, and I think now it's stronger and stronger evidence that that's because just the brain idea that just makes the neurons get hooked up in the way you need to be expert in that subject. And so to that extent, that would argue that the same basic ideas would apply in any scholarly field. When you get down to our list of specific decisions and practicing those, it gets a little fuzzier. But every field I've looked at, and I have looked at history, and I've talked actually and some people in classics and so on. And if we talk in detail about how they do some problem in their subject, you can see the same sets of decisions coming up. In history, for example, you still have to ask, what are assumptions you can make? What can you not neglect? What's information you need to make an argument? What is you have to decide the credibility of that argument and how to decide and determine it. And if you go through the whole list, almost all of them, there's a few kind of mathematical ones, but almost all the others you see very directly apply. And so I suspect that almost all of these would apply in much the same way across many fields, but we really don't have the data from teaching cases that do have a side-by-side comparison like we do in science and engineering. The next question is, why do so many physicists seem to disregard educational research, and how do you think we can tackle this problem? That's a very complicated question. I mean, at some level, there's a lot of education research, and there certainly in the past, which wasn't very good, just like in the early days of physics. There was a lot of research that wasn't very good. And so it's not complete, in some sense, this kind of research I'm talking about is a much younger, less mature field. And so it's not unreasonable to have some amount of skepticism about it. But more fundamental with that is it's nothing special about physics. It's anything that people have been doing for a long time. They're very resistant to change, and very resistant to change on the basis of research. And you see that kind of across humans and human culture. That's kind of what culture is all about. And so I think it's really an issue of a cultural aspect. And how do you tackle this problem? Well, that's what I spend my life worrying about, of reaching out, trying to get data that will convince people, trying to get the best evidence and so on. But ultimately, I think it really requires us to complete a fundamental rethinking of education. And so it's not a physics problem. It's really much broader than that. It's the, universities and society thinks of education as putting knowledge into this receptive brain, as opposed to no, high-level education is about developing that brain. And so that's going to really take, in some ways, a much broader sort of reevaluation of education and what it's providing. And, I think you just have to say, look, there's lots of areas of research where it took a long time for societies to change, and you just have to keep working at it. Okay, so this is a really good question about grading and exams. So there's no easy answer to this one, because again, we have systems that are so based upon exams and grading that you can't simply make declare you're not going to do this anymore, because it just can't. Universities just wouldn't be able to function. And so there are things we know that you can do better. Oh boy, somebody's changed the sound, so now I'm getting a whole bunch of echoing. I hope you're not. Whoever switched it so that I'm now seeing myself twice as opposed to the auditorium, can you switch it back? Some technical person. Oh, well, I'll try and go ahead and answer this. But so one of the things to think about is, I guess I look at it as, how do we make exams and grading more meaningful? And so the first thing to recognize is what the typical exam is testing is so different from the thinking you want people to learn. You go, so much of an exam, you're given all the information you need and only the information you need. There's no authentic physics problem that has anything like that. And so I would argue you want to start by thinking about, how can you make open book, open anything exams, because that's where the real world operates. And then you've got to think about problems that are still meaningful, but students have to make actual judgments and decisions and justify those decisions like a physicist. And so you start by making your exams that way. But the other aspect that we do know is that exams, if they're just kind of measuring whether a student succeeds or fails, that provides no educational value. And if you want to have them provide educational value, you have to think about, how can they be providing feedback to the student to learn? And so there's several ways to do that. One of them is to just have many more lower stakes exams. So you think about it as sort of a lot of little quizzes where people take the quiz, learn what they did and didn't know, and can use the results of that quiz right away to improve, to focus on how they can learn better, guide their studying. So that's one aspect of it. The other aspect that I don't have any research to justify, but that I just my own personal bias is that because I know that exams don't really measure anything very meaningful, and I say that is a research statement. I've done a lot of looking at that. I tend to try and grade things that basically reward students for doing the kinds of activities that I know will improve their learning. And so, yes, there are multiple low stakes quizzes, but there's also homework and other activities and studying where if I'm confident from the research that it's going to improve their learning in the subject, then I'm fine with giving them grades for just doing it. And one other final thing is that people, and including my own group, have found success in things where it'll be a two-stage exam where the students will first do the exam individually, and then they'll work through it again in small groups, where the group almost always can get all the answers right. And the students learn a lot from that process. Almost anything they got wrong initially that the group gets right, they really remember that much better than if they just took an exam and saw their grade later.
Bueno,
So yeah, so I see the question is, what do I think the results of your research can be applied to Colombia or other countries where education and socioeconomic gap is really significant? You know, I'm stretching here, not being terribly familiar with the Colombian system and so on. But if I look at what works in the US across the educational spectrum and the student spectrum, you know, we do have substantial socioeconomic inequities. And what we see is that these certain things work, you know, what works for one group of students works for the others. And the differences come in not to the basic instructional design and principles. Those seem to be really matched with how the brain works. The differences come in that figure I showed you, the motivational aspect and the prior experienced aspect, that you have to think of what kind of tasks you're giving the students and questions that motivate them based on their experiences, what they see as worthwhile and useful to learn for them, and that address things, you know, build on what they and are properly appropriate for their background experience and knowledge that they start with. So, you know, what we see, I think, is that that's where your differences in background and experience come in and have to be addressed in different ways, but the fundamental learning concepts, teaching concepts are much the same, I believe. Okay, what are your thoughts on saturation of physics academic jobs? What suggestions would you be to physicists in formation scared of the future? That's outside my area expertise, and so I won't even try and answer it. Any of you could answer that just as well as I could. I don't know.
Hola, nuevamente agradecerte pues, por la charla.
Once again, thanks for the presentation.
Soy estudiante de Ingeniería de Materiales en la Universidad de Antioquia
Materials
y
engineering student
Física
at
en la
University of
Nacional.
Antioquia.
Y hace
Can
poco
you hear me okay, Mr. Wieman?
me tocó
Yes.
una técnica
I
de
have a lot
estudio
of
de
I have
un
a
físico
huge
pues,
echo.
también ganador del Premio Nobel en 1965, muy conocido, que es Richard Feynman.
Another Nobel
Y él
Prize
tiene una
winner in
técnica de
1965.
estudio
He
que se ha
has a
extendido por
study
todo,
technique
pues es muy
that
conocida en
has
muchas
spread
universidades. Y
to
pues lo que
many
quería preguntarte era,
universities.
¿qué opinión tienes acerca de esta técnica de estudio? Si la has escuchado,
My question is, what's your opinion on that
pues,
study
si la
technique?
efectividad que ha tenido en los estudiantes.
About how effective it has been on
Así sería
students.
esa sería la pregunta.
And again, that's my question with regards to that.
What is the teaching technique? I didn't hear that.
La técnica de estudio de Richard
The
Feynman.
study, Richard Feynman's study technique.
Oh, Richard Feynman. Yes. Okay. Yeah. So I'm very skeptical of Feynman. I think Feynman was a classic performer. And so he could entertain people. People who are already expert physicists love his explanations and way of talking about things. I think there's very little evidence that he was effective at effectively teaching introductory students. And what I've heard is that in his classes, actually, most of the students stopped coming.
Hola, hola, hola. Soy Joshua Giraldo, estudiante de astronomía, y quería preguntarle si en sus investigaciones sobre educación hay cosas que se pueden aplicar a la comunicación científica, a la divulgación, en la que el grupo objetivo al que se pretende enseñarle no tiene bases científicas como usted comentó, que es uno de los pilares principales en el método que usted nos ha
That's
presentado.
one of the main pillars on the method that you were describing to us.
Yeah, I mean, the ideas that I talk about here really are directly applied to science communication, because at one level, communication is about teaching, and so the same ideas all apply, and at every level you kind of have to match your level of presentation to the knowledge that the people have, and that varies to different groups, but otherwise the concepts are much the same. The principles are much the same. I don't know how it sounds at your end, but oh, now it's not working. Now I'm getting more.
Hola, buenas tardes a todos. Inicialmente también agradecerte por la charla, fue una información bastante interesante y de aprendizaje. Yo soy estudiante de astronomía de la Universidad de Antioquia y también soy ingeniero en ciencias computacionales. En ese orden de ideas, mientras daba la charla me surgieron un par de inquietudes, sobre todo en la forma en la que presentaste el framework de enseñanza, porque inicialmente hablaba sobre cómo desarrollar estos hard skills, estas habilidades duras a través de la enseñanza, pero hay aspectos relacionados a temas socioemocionales o aspectos humanos como lo son la motivación, la proactividad, la comunicación, que es justamente parte de algunos estudios que hice en el posgrado. En ese caso me gustaría saber un poco más del background con respecto a estas habilidades blandas mínimas, o si como parte del estudio que ustedes hicieron identificaron un conjunto de soft skills que se pueden aplicar de manera transversal, como bien lo mencionabas, para poder aplicar este framework en cualquier otra área del conocimiento. Sí leí algunas en la presentación, pero me gustaría conocer un poco más si parte de ese estudio toma algunas otras que no hayas mencionado, y cómo afectó esto la forma en la que se aplicó el método durante el tiempo que lo llevas realizando. Gracias.
How this has affected your research.
So I'm just trying to think about that. There's parts of it which I'm not sure. Nod if you can. Okay. I don't understand why this keeps changing. You know, computers are supposed to keep working the same way unless somebody throws switches that are wrong. So, okay, the soft skills. So, I'm not sure whether this would be a soft skill or not. But we do study what motivates people, and we do get research on motivation and how to design instruction to better motivate people. We look at the interactions in these small groups, and we Okay, we look at how the small groups interact, and we study different practices that optimize that, and we essentially assist students with communication. Can you hear me now? Okay, so I'll just finish with, we do look at aspects of communication between the students and basically, how to listen properly and how to collaborate well. So I guess that's sort of a soft skill, but it really supports it supports the learning very much too. So those are aspects that we see are important there. Okay, so I'm inclined to just, if we can just keep the settings like they are now, and I can see questions through chat and then answer them. Maybe that's the best way to go. So I will wait till I see something more on chat, I hope.
I'm not sure if we're waiting on the translator. Can you hear me?
I can hear you.
Okay. There's one question that's been on YouTube and it's been here and it's all around. And I also have it myself. What are your thoughts and what can you share about FET interactive simulations, and how can it be applied to university teaching? Thank you.
Okay, so glad to say a lot about that. I mean, those of you who aren't familiar with it, it's these interactive simulations are used very widely. And those are good in that they, I'm trying to think how to explain this in terms of what I was talking about. What we see is, okay, the way people learn is, or to be an expert, you have these mental models of a system and what the variables are and how they interact. And you use those models then to make predictions, to make interpretations, and so on. And so what the FET simulations do is they just provide a much more useful tool for having students grasp or develop that mental model of what are the parts, how do they interact, and so have lots for mechanics and E&M and so on, and so for particularly, I showed that example that we use in class of what the light bulbs and the batteries, okay, and so what one can do is in the FET simulation, you can actually see the electrons moving around through them, little cartoon electrons, and you can see how as you change the voltage or you change the resistance or you open and close switches, what happens to those electrons. This gives people a much better idea or much deeper conceptual idea of what electricity is and how it works. And then you can even couple that with quantitative measurements that you use the simulation to do. In many regards, it's almost certainly, or in most regards, it's almost certainly more powerful than actually hands-on equipment for understanding the underlying physics, understanding the quantitative relationships that things have. And so these, we've got lots of those for introductory, but even I use the quantum mechanics simulations are tremendously powerful for understanding the basic concepts in quantum mechanics. There's really no kind of educational medium that comes close, because in quantum mechanics, so much of it is differential equations to solve the Schrodinger equation. And you got to do a whole bunch of cranking differential equations to basically get any kind of intuitive understanding of how system behavior. And with the FET simulations, you've got that there. It's really doing the solutions for you, and you can get a much more immediate, deeper understanding of these very challenging concepts. And so that's just an example where it simply provides an educational tool that has capabilities that nothing else has. And so that's useful, plus the fact they're free and to everybody. So.
Which has been amazing, by the way. I think we can all agree. People are asking regarding students who are not interested in the class, either that, or who are not interested in new ways of learning or new methodologies. Who say they have this resistance to changing the way classes are generally taught. So what are your suggestions for those kinds of students? How can we encompass them as well?
So, because I'm not sure how the sound is going to work, I'm going to refer to the, I'm going to try something here, see that. I'm going to refer on I'll make my slides available, and that CWSEI website has a brief note about this, but this is actually an area we've studied, of getting students to buy into these different ways of teaching than what we've seen before. And the quick way to say it is, I'm just summarizing a bunch of steps, but we really bring them into the process and try and show them at the very beginning why the teaching is being done this way, because it's more beneficial to them, that the research data evidence on illustrating that, and the principles behind it, sort of a short version of this kind of talk, and giving the students a chance to ask questions and discuss it actually, and so that they don't feel like they're guinea pigs that you're doing an experiment on, but you're sort of working together to maximize their learning and their success. And basically, we found that's quite successful, but it is essential, really, to be quite explicit about that, particularly if they haven't experienced this kind of teaching before. Once you start getting a number of courses being taught this way, they're used to it, then they start complaining when they're not taught that way, because they start complaining that they're not learning nearly as much in their classes, and they want the better use. But that comes only after you have multiple exposures and they're sort of used to it.
Thank you. We're going to leave the questions at that. We are incredibly grateful with you, Mr. Wieman, for your time, for your patience with all the technical issues. Even now, I'm expecting like a loud noise to startle us. But like for us in Colombia, and right now we are experiencing a historical moment. We're thinking about change, we're thinking about truth, we're thinking about education and the challenges we have as academia. So once again, all your words are really greatly received. And everybody here, I'm sure we had an amazing educational experience, even, I don't know, the technical team, that's also hands-on learning. So nothing is lost. We try to make the biggest event possible for Mr. Carl Wieman, 2 transmissions at the same time, and a bunch of stuff can happen. So once again, thank you for your patience. Thank you for your time. I want you all to give a giant round of applause to Carl Wieman. And for you people at home, also thank you for your patience and thank you for being here and asking your questions. This is a very important moment and we are very grateful with your presence here, Mr. Wieman. So thank you very much from the University of Antioquia, from Colombia, from the students. I thank you.